Hello everyone and welcome to lecture. In today's lecture we'll be talking about generalizing the concept of vector spaces, which we've already seen a number of different examples of, but I don't imagine, and you may have seen examples of an infinite dimensional vector space. I guarantee you've seen a number of examples already and just not known maybe that what you're actually dealing with is a vector space. So we'll start off by defining what a vector space is and give some examples of infinite dimensional vector spaces. And then once we kind of set down a definition, we'll be able to go through and generalize a number of different concepts that will be very, very useful to us as we proceed into what's known as the topic of Fourier series, which is a hugely important aspect and example of applied mathematics in engineering. So to begin, let's start by defining what a vector space is. So recall that a vector space over a field F typically F can be taken to be the field of real numbers or the field of complex numbers. It could be taken to be a more complicated field as well. But we say that a vector space over a field F is a set V together with two operations that satisfy certain axioms. So this is both of these two operations satisfy certain axioms. The two axioms here are, or the two operations, are called vector addition and scalar multiplication. And the axioms are the following. Axiom 1 is called associativity of addition. And this means that for any three vectors u, v, and w in the set V, u plus v plus w is equal to the same vector as u plus v plus w. Axiom 2 is called commutativity of addition. And it says that for all u and v in the vector space V, that u plus v is the same vector as v plus u. Axiom 3 of the vector space is called sometimes called the identity axiom. Or the existence of an identity element axiom. And this is saying that there exists some vector we call the zero vector in the vector space V, such that for all v in the vector space, so for any vector in the vector space, v plus 0 is equal to v. And I should be very specific, it's the identity element for addition. Axiom 4 is the inverse element axiom for addition, or of addition. And this states that for any element v in the vector space V, there exists an element that we sometimes denote minus v in V, such that the vector v plus minus v is equal to the identity element, the additive identity. Axiom 5 deals with compatibility of scalar multiplication with field multiplication. So it deals with scalar multiplication. And this simply states that for all constants a and b in the field F, and for all v in V, if I look at the scalar multiplication of A with the vector BV, this is the same thing as scalar multiplication of A times B times V. So multiplication operations are in some sense only valid in terms of a scaling operation on the vector, and this is compatible with the scalar multiplication in the field F, which is guaranteed to have nice multiplication properties. Axiom 6 is that there is it's in regards to the identity element of the scalar multiplication. And this is that we know because F is a field, there exists an identity element multiplicative identity element in the field F, and the results of multiplying this F by any vector, this identity element by any vector in V, will give us the vector V itself. So it's any vector is unaffected by taking the identity element in the field and multiplying it by a vector. And then we have two more axioms. So the last two axioms deal with how vectors behave in relation to addition and multiplication with field elements. So the first, we have axiom 7, which is in regards to distributivity of scalar multiplication. With respect to vector addition, and this is just saying that for any element A in the field and for any vectors U and V in the vector space V, the scalar product, or the product of A with U plus V, is going to be equal to A scalar product of A with U plus the scalar product of A with V. And then our last and final axiom is axiom 8, which also deals with distributivity. This is distributivity of scalar multiplication with respect to field addition. And this is just that for any two scalars in the field, and for any vector V in the vector space, A plus B, so the scalar multiplication of A plus B times V, is the same thing as the scalar multiplication of A with V plus the scalar multiplication of B with V. So these 8 axioms really serve to define every axiom that is needed that is satisfied by any vector space, no matter how complicated it might be. And right, we've already seen a number of different examples of vector spaces, and been working with vector spaces for a while now in terms of n-dimensional space, Rn. Or in the vector calculus, we really kind of focus on vector calculus in 3-dimensional space, so in R3. But a great example to go through is go through and check that these axioms hold. In any n-dimensional Euclidean space Rn. And it's a relatively straightforward exercise to go through and do that. So I want to make a note here that vector spaces found in engineering or used in engineering are typically taken to be over a field of real numbers or complex numbers but really any field can be used to define a given vector space. Now, typically in a linear algebra course, you study transformations from Rn to Rm, and this has a lot of connections with what are called linear transformations from Rn to Rm. In vector calculus, we've kind of been studying nonlinear transformations from Rn to Rm. But the idea is that what we're going to be doing is looking at kind of extending our idea of a vector space and seeing that a vector space can actually be, we can have infinite dimensional vector spaces. Rn or Cn are both finite dimensional vector spaces, but we can really view these spaces in a more general manner. And notice that when we define the vector space here, we don't go through and actually specify or define the dimension of the space. So this space, the set V, can really be any kind of set as long as it satisfies the axioms inherently defined for the vector space. So case in point, one of the big examples that we'll see is that if we define C, Rn or Cn is a vector space, you can go through and verify the axioms for either of these two spaces. That'd be a very, very good exercise. But a good example of vector space that we'll be considering a lot in the next couple lectures is going to be the set C of I. This is the set of continuous functions from I to R. So continuous real-valued functions. For the set of functions, such that f is a function mapping some interval to the real numbers R, where we'll call I here, we could also call I here the interval from A to B. And one of the things that you'll see is that it's relatively easy to go through and verify that this is a vector space by checking all the axioms. So for instance, let's assume that f and g are two elements of a set of continuous functions from the interval from A to B. We know that f plus g, defined as f of x plus g of x, is going to be continuous because f and g are both continuous functions. And we also have then that if C is any real number in R, then the function c times f of x is equal to c times f of x, which itself is a continuous function on the interval from a to b. The zero function we'll call it theta of x, is just the function that's defined by theta of x is equal to 0 for all x in the interval from a to b. This serves as the additive identity, right, for any function f of x plus theta of x would just be equal to f of x itself. And we can also note that I've only got a couple of the axioms here, but if you go through and check all the other axioms, this function space, or the space of continuous functions, is in fact a vector space because it satisfies all of these axioms right here. The elements of the vector space are functions, right? But even so, right, these things we can think of as vectors inside of a vector space. Now, note that, unlike the examples of Rn and Cn, where Rn has dimension n, and Cn, so it's complex numbers, or the Cartesian product of the complex numbers, has dimension 2n, but these are both finite dimensional vector spaces. The space C of I is an infinite dimensional vector space. But it's still a vector space. It just doesn't have a finite dimension. And it turns out that the concept of Fourier series and a lot of related concepts that we'll be talking about are very, very closely related to the idea of understanding infinite dimensional vector spaces. So it turns out that many of the examples that are developed for finite dimensional vector spaces that you would see in a basic linear algebra course are almost directly applicable to infinite dimensional vector spaces. They just require a little bit more proof and a little bit more subtlety in terms of how we make these extensions. And the first concept that is going to be very important to us is the concept of linear dependence versus linear independence. So we'll start by defining linearly dependent or linear dependence. This is one of the first concepts that we'll see extends directly without any real modification to an infinite dimensional vector space. So we'll start by defining that. So we say that a set of vectors v1 to vn in the vector space V is linearly dependent if there exists field elements or scalars C1 to Cn in the field, not all 0, so at least multiple field elements have to be non-zero in the C1 through Cn, such that the linear combination of C1 V1 plus C2 V2 all the way up to Cn Vn is equal to the 0 element of the vector space. In other words, we say that this set of vectors is linearly dependent if any one of the vectors in this linear combination of not all 0 values can be written as a linear combination of the other vectors, right? So if these are all non-zero, or even a subset of these are non-zero, say C1 is non-zero, C2 is non-zero, and the rest are 0, then you can express, so C1 is non-zero and C2 is non-zero, you can express V2, the vector V2, as being equal to C1 over C2 times -1 times vector V1. So in this case, vector V2 depends linearly on V1. And this is the basic idea of linear dependence. This should be a very familiar concept for you if you studied linear algebra, taking a linear algebra class. On the other hand, you see that a set of vectors V1 to Vn in the vector space V is linearly independent if the equation C1V1 plus C2V2 plus CnVn is equal to 0 can only be satisfied if the coefficients C1 all the way to Cn are 0. And this implies that no vector in this sequence of vectors can be represented as a linear combination of the remaining vectors in the sequence. And I want to note that we have now a significant difference between an infinite dimensional vector space and a finite dimensional vector space, which is actually in some sense a characteristic of the fact these two types of vector spaces are different from one another. So if you take n-dimensional Euclidean space, Rn has a finite number of basis vectors meaning that we only need n basis vectors, where n is the dimension, to find a linear combination representing any vector in Rn. However, an infinite dimensional vector space has no such finite basis. So for example, if you consider the vector space V of polynomial functions of the interval from A to B, I'll first note that this vector space V is a subset of the space of continuous functions on the interval from A to B. But there's no such basis, finite basis I should say. Because if you take P naught of x to be defined as the function 1, P1 of x to be the function x, and so on and so forth, all the way up to Pn of x, the function x to the n, you can represent any general polynomial, I should say any general nth polynomial, nth degree polynomial, as c1 times 1 plus c2 times x plus c3 times x cubed, all the way up to cn times x to the n. But there are still more functions, and there are infinitely more functions in this vector space, because we're missing all of the polynomials that are of order higher than n. It's also important to point out that in a function space like this, the linear independence and dependence relation, if you see you have f1 to fn in the set C of AB, the space of continuous functions from A to B, C1 f1 plus C2 f2 up to Cn fn is equal to 0, the zero function. This is the same statement as saying that C1 f1 of x plus C2 f2 of x all the way up to Cn fn of x is equal to 0 for all x in the interval from A to B. But this is a very interesting and important example that we're going to come back to and see a lot of. So up to this point, what we're seeing is that functions, in some sense, functions that are real valued or even complex valued, we'll see. But functions that go into a field can be viewed as, in some sense, infinite dimensional vectors. So, say for a vector x in R4, this is something that looks like x1, x2, x3, x4, where x1, x2, x3, and x4 are all real numbers. Correspondingly, if f is a function in the set CAB, right, then we define this function f by how it behaves on an element x in AB, the interval AB. So just like we kind of think of a vector as having components, if x is a vector in R4, then x has components x1, x2, x3, x4, where each one of these is a real number. And we can think of a function as being a vector in this infinite dimensional function space, or infinite dimensional vector space, where the values of this vector are indexed by the value x, whatever x is. This is a very useful way of thinking of this idea. And it's actually a very beautiful way, I think, of thinking of this idea, because it extends pretty much all of the topics from a linear algebra class, typical linear algebra class, to this new realm of applications. So we can introduce an inner product or dot product for functions in this infinite dimensional vector space. By remembering what we know about integration. So is it the inner product or dot product? There's a number of different notations for this. We have f comma g right here. And this is assuming that f and g are both vectors or functions in the vector space of continuous functions. The book that we're using, Engineering Mathematics, introduces the normal dot product notation that you're familiar with for normal vectors. But we introduce this as the integral from a to b of p of x times f of x times g of x dx. And I should be specific here. This is an inner product or a dot product. With a weight function P of x. Where P of x is continuous, P is in a set of continuous functions, and P of x is positive for x in the interval from a to b. The open interval from a to b. And this is just a little bit of generalization that we'll end up using later. But for all intents and purposes, right, this gives us a dot product, an inner product. And it gives us all of the properties that we expect from a normal dot product. So I recommend going through and showing this, but the first main property that you'll remember for the dot product is that the dot product of f with g should be equal to the dot product of g with f. Or the dot product is commutative. We can reverse the order in which we take the dot product. And this is just because this happens, this is satisfied because the integral from a to b of p of x, f of x, g of x dx will always be equal to the integral from a to b of p of x times g of x, f of x dx. And we have a number of different other properties as well that I'm not going to prove, but are relatively straightforward to go through and show using your basic knowledge from even Calculus 2 course. This is that the inner product of f plus g with another function h. So here we're assuming f, g, h are all in this vector space of continuous functions, and we're assuming that c is some element in the underlying field f, but the dot product is distributive, so the inner product of f plus g with h is going to be equal to f, inner product of f with h, plus the inner product of g with h. For any c, c times the inner product with f in g is going to be the same thing as the inner product of c with f in g, and this is the same thing as the inner product of f with the function c times g. And 4 is that for any function f, the inner product of f with itself will always be greater than or equal to 0. And the inner product with f with itself is equal to 0 if and only if f is equal to the 0 function for all x in the interval from a to b. And these properties can all be shown using standard integral properties. So I know I said I wouldn't prove any more of these, but I will go over 4 just to kind of take home this message that we're going to be going over and kind of using a lot of. So if you take, for instance, the inner product of f with itself, you end up getting the integral from a to b of p of x times f of x squared, and p of x times f of x squared. P of x is a positive function. F of x is not necessarily positive, but f of x squared will always be a positive function. So this integral will always be greater than or equal to 0. That the accumulation of the integral of a positive function will always be greater than or equal to 0, unless f of x is identically equal to the 0 function for all x in the interval from a to b. Because we're assuming that our weight function p of x is a positive function. So this is a very, very cool idea because it shows that for the space of continuous functions, and really for many vector spaces, where we can define some concept of integration, we also get hand in hand a concept of inner product or dot product between infinite dimensional vectors. And if we have a dot product, then we can also use this idea to construct what we call a norm of, or length of a function. In some sense, the size of a function. So this is in view of property 4. We can define a norm. And we say that the norm of a vector, or I should say a function, in the space of continuous functions on AB is defined as the norm of f. And this is why we used that norm notation before. This is a different norm notation than we used before. This notation for vectors in vector calculus, we're dealing with vectors in a finite dimensional vector space. So this is a new norm for functions or vectors in an infinite dimensional vector space, where integration is defined. We define this as the square root of the inner product of f with itself. Which in terms of an integral is the integral from a to b of p of x times f of x squared dx, the square root of this. And you can think of this as being, in some sense, the size of the function f in this infinite dimensional vector space. Now, there are other ways of introducing norms in a vector space, an infinite dimensional vector space, just like there are other ways of introducing norms in a finite dimensional vector space as well. But we'll be strictly focused on this definition of norm, and above this definition of inner product for functions in a function space. Because this is kind of what we'll be moving into is Fourier series, and this concept is very, very important in Fourier series. But using this idea, you can also define a concept of distance between two functions. The distance, let's say distance in quotations here because we're dealing with an infinite dimensional vector space between two functions f and g in the space C of AB is defined to be the norm of f minus g, or d of fg is equal to the norm of f minus g, which is the square root of the integral from a to b of p of x times f of x minus g of x squared. And so this is also a very cool idea because it is a direct method of essentially giving us, in some sense, a way of defining the closeness of two functions or two vectors in an infinite dimensional vector space. So really we'll be focusing on vector spaces that are either C of AB or subsets of C of AB, because this is where our application to Fourier series is going to be, or the application of Fourier series is going to be really important. So we have a dot product or an inner product, we have a norm, and the next concept, if we continue the analogy with n-dimensional space, we can use the dot product to define what it means for two vectors in an infinite dimensional vector space like C. So it's continuous functions with this inner product that we've defined above to be orthogonal. So we say that two functions f and g in the space of continuous functions from a to b are orthogonal if their inner product is 0. So if f dot g is equal to the 0 function, this means that the integral from a to b of p of x times f of x times g of x dx is equal to 0. And this is very, very neat because it's these three definitions give us essentially a way of thinking about an infinite dimensional vector space, like the space of continuous functions from a to b, in terms of geometry or geometrically. We can talk about orthogonality of vectors in an infinite dimensional vector space like C of A, B. We can talk about distances in this infinite dimensional space. And this is a very, very, very useful idea. I really can't overstate how useful these concepts are going to be for us. So let's go over some examples, and we'll kind of look to some examples to kind of guide us along.